In this video we're going to talk about timers and counters. But before we go any deeper into microcontrollers and getting into timers and counters, we really need to start talking about binary, decimal, and hexadecimal. And you'll start to see how decimal really doesn't fit in the world of microcontrollers. Binary and hex really do go well together. It all comes down to what can fit in digits and digit spaces. So let's say we have a binary number here, and these are just digit spaces. This would be considered a 4-bit binary number. It has 4 different spaces, and the bit is equal to, 1 bit is equal to 0 or 1. The bit is considered base 2. Our decimal in decimal system is considered base 10 because we can fit 0 through 9 in one space. So in decimal, one space you can fit 0 through 9. In hexadecimal, in one space you can fit 0 through 16. Actually, it's 0 through 15. 0 through 15. That gives you 16 different numbers. This gives you 10 different numbers. And one of these gives you 2 different numbers, 0 or a 1. So how do you count in binary? Well, let's try some. Let's start with a 4-bit number, which is 4 places. Okay, so we can start out with 0, 0, 0, 0, which would be just equal to 0. To increment in one binary number, you would put a 1 here, obviously, because 1 plus 0 is 1. But how do you get into the next digit? Because there really isn't any other numbers. We can't go to 2. So for the next number, we just put in 0 and then 1. So in base 2, this would equal, well actually let's just do each one. 0, this is 1, this would be decimal. And this would equal 2. Now to get number 3, we're going to do the same thing. We're going to go increment this digit by 1, and this one stays the same. And it would go along in the same fashion to go to number 4. Just like we had the dilemma of not knowing what to do here, we have a 0, and then we're going to have another 0 here because there's no other numbers you can fit in the second digit, and we're going to put a 1 here. So we're now using the third digit. And for number 5, we start all over again. This is going to be a 1 because we're incrementing 1 to this one. This is going to be a 0 because we don't need to use any other digits, any other spaces, because this has the capacity for a 1, and we just have a 1 here. Number 6, we do it all over again. This is going to be a 0, and then we're going to add a 1 here, and then this 1 maintains. And then 7 is going to be 0. It's going to be a 1 because we're adding 1, and then this is going to be a 1, and then we have another digit 1. And when we get to number 8, we're going to do this whole process over again. 0, 0, 0, and then 1. In a 4-digit binary number, we're already almost at capacity here. This is halfway through. We're at number 8. And if we had the binary number as 1, 1, 1, 1, we would be equal to 16 in decimal. But this is really inconvenient because we're using 2 decimal places in decimal. We're using 2 digits in decimal. And with a 4-bit number, we could actually use a number that is base 16. And base 16 is hexadecimal. Because in base 16, we're only going to be using 1 digit. So it would be really convenient to have a 4-digit number in binary equal to a single digit, and that would be the hexadecimal digit. Unfortunately, humans aren't really used to using base 16 as a single digit number. And we really don't have any symbols in our human terminology for base 16. So what they had to use is they had to use letters. In hexadecimal, 0 through 9 is still a hexadecimal number. But then we have to go all the way, and we have to add more digits to get to the 16th number. So we use A through F. So let's write 16 digits in decimal. That's 0 through 15. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, now we're running out of decimal digits. So we have 10, 11, 12, 13, 14, and 15. So now we have 16 different numbers from 0 through 15. Let's write the hexadecimal equivalent. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and now we're in our knowledge of decimal, we have to go to the next digit, but in hexadecimal, we can start with A, B, C, D, E, and F. So what we've done is we've maintained a single digit for a 4-bit binary number, which is 1111. So now you know a little bit about why hexadecimal is very compatible with the binary number system. So let me give you a little bit more of an example of why it's really helpful. Let's show many binary 4-digit numbers. Okay, that's 4. And when you put another one next to it, now you have two 4-bit binary numbers. This is a 4-bit, and this is a 4-bit. Altogether, you have an 8-bit number. In hexadecimal, this would be a 2-digit number. This would be the first digit, and then this would be the second digit. In decimal, this would actually come out to be a 3-digit number at the maximum number, 256 places, or the maximum decimal number of 255. But in hexadecimal, this would be an F to the maximum number, and this would be an F. So this would be represented as 255 in decimal, or in binary, it'd be 11111111. So now you can see that the hexadecimal is very compatible with the binary, and it's kind of incompatible with the decimal. This is just like sort of some arbitrary number. I learned through decimal as I was growing up in learning binary and hexadecimal and decimal. So I got used to a lot of these weird numbers like 255 and 32,767 or 65,535 or so on and so forth, or 1024. So we really don't want to mix into the decimal. If you can avoid it, try to stay away from decimal and use hexadecimal because it's a little bit easier to understand. And you've seen this before if you have worked with numbers, or if you've worked with colors with, say, Windows or any other operating system, and that comes in red, green, and blue. And these are the colors that you would mix to get any color of, let's say this one. In decimal, you'd have 256 variations. In green, you'd have 256 variations, and in blue, you'd have 256 variations. And mixing all these numbers, this is 256 times 256 times 256, you'd get a number in the 16 million range. 16 million something. 777, 216. So you'd have a number that, and you've probably heard this, each pixel would have 16 million variations, or 16 million depth of color. An easier way to represent this would be using hexadecimal. The maximum number you can have is FF for this one, and you've seen this in Windows before, FF. And if you look at any color, you have FF. And the way it's represented, you'll start to see how this is like a number to represent a particular color. Generally, they'll put a number sign before it. When you look at programs online on some code examples for microcontrollers, you'll see a lot of the hexadecimal numbers. And you have the option of showing this number in either hexadecimal or binary. It's up to you. But you have to be able to understand what other code is saying, so you can actually take a hexadecimal number and really understand what the binary number is, what they're trying to portray. And all you really need to know is this amount of information, a 4-bit number, how to get a hexadecimal out of 4 bits. So let's go ahead and just do a 4-bit number. We'll do the 16, 0 through 15 numbers in hexadecimal and binary. We'll just do a chart, a sequence from 0 to 15, which is 0 to F in hexadecimal, or it's 0 to 1111 in a 4-bit binary number. Once you have the understanding of the hexadecimal and the 4-bit binary number, you can put those together to make an 8-bit. You can put those two together to make a 16-bit and a 32-bit or a 64-bit, and then it becomes very easy to understand the hexadecimal number compared to a binary number. And you can also see how decimal really does kind of suck with working with microcontrollers and understanding the number system. So don't worry about getting into the decimal number system. So we'll start with the binary here, and then hex here. So we'll have the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So we'll start here at 0, hex. We'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So we have 16 numbers here. Okay, so of course the 4-bit binary number is 0, 0, 0, 0 for 0. For 1 it will be 0, 0, 0, 1. 2 is 0, 0, 1, 0. You're also going to see a pattern here where 2, 4, 8, and actually 16, which you're not going to see, actually has a kind of a pattern. It's where these ones actually move to decimal places to the next digit. So you have, this is 2, you'll see the 1 and then a 0. Then you'll have 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. Then you'll have 1, 0, 0, 0, and that you'll see is at the 8th place. That is at the 8th place. And then you have 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and then you have the last number, which is 1, 1, 1, 1. 16, if we were to go all the way to 16, which is 17th digit, would be the 1, 0, 0, 0, 0. So you can start to see, this is the division line here, you can start to see where 16, 8, 4, and 2 have some kind of similarity, and that is 2 is equal to 2 to the power of 1, 4 is equal to 2 to the power of 2, 8 is equal to 2 to the power of 3, and 16 is equal to 2 to the power of 4. Now that we know a little bit about binary numbers and hexadecimal numbers, we can talk a little bit about the timers. In this video I'm just going to cover a small portion of the timers because it's actually quite complex. There's quite a bit of information or the capability with the microcontroller with timers and counters and how they work with the internal clock and how they affect the pins of the microcontroller. We're going to pretend that this square here or rectangle is the microcontroller and just pretend it's a box. There is an internal clock. I'm just going to make this look like a regular clock, and in the microcontroller, the ATmega32, it counts or it ticks at 1 megahertz, which means it ticks 1 million times per second. I'm going to introduce you to Mr. TCNT. Actually, this is Mr. TCNT1, and there's also a TCNT0, which is an 8-bit. Mr. TCNT, all he does is count. And Mr. TCNT counts with the internal clock. However, Mr. TCNT can only count up to 16 bits of binary numbers. And 16 bits, if you remember back, talking about the binary number system, 16 bits is actually 65,535 in decimal. In other words, he wouldn't be able to count up to 1 million clock cycles. So you're probably wondering, how would we be able to get the timer to count in seconds? I'm going to show you one way to do that without having to be able to count up to 1 million. And there's also something called prescalers that I'll introduce you to later on. Just to give you an idea of some of the features that you can get with the timer and counter, you can have the timer and counter react, or you can have it react with a pin, with a signal coming in. You can have it controlling a pin, and that is giving a signal out, a pulsing signal. You can also have, you can say, I don't want to use this clock, and you can connect another clock to a couple more pins. Generally, the clock that's inside of the AVR is not as accurate as an external clock could be. The clock that's inside the AVR is about 10%, has an error plus or minus 10% of its timing. The clock that's external could use a crystal for much more accurate timing, like a quartz crystal that is used in clocks or watches, and it will give you much more accurate time. But right now we're just going to use the one that's internal. We're not going to be controlling any pins or receiving any pulses, and we're just going to be counting and maybe turning on and off an LED or a series of LEDs. What we're going to do is make a simple LED array, and we have this actually from the previous video doing the button game. I removed the buttons, and this is counting in seconds. You can see that this is just toggling from one LED to another, and it is going from one LED to another every second. And this one is every 1/7 of a second. You remember we had 7 of these LEDs, and it'll just chase from one to the other, and then this one will change. This is all going according to the internal clock, which is actually asynchronous to the core of the CPU. So those two processes can run simultaneously and not really bother the CPU any, the actual core of the CPU. Now, there's the few applications that that you could think of using the timer is obviously a timer that counts down and then it gives you an alarm at the end of the count. But it could also be used for things like when you're measuring data. You want to make sure that when you're doing the measuring of data, it's done, and if it has, and time is a very important aspect of it. You want to make sure that when you're measuring data in different circumstances, you want to make sure that the time that you do those data measurements are constant. So if you're going to take some, say, measurements for a time span of 10 minutes, you'd want to do that with all of the measurements, and you would want your CPU to be able to time that. Just to get familiar with what we're dealing with, this is the data sheet for the Atmega32, and what we need to do first is we need to use the timer counter control register. And this is really just a register that controls the timer and how it behaves. And you'll also notice that this is the 16-bit timer counter register. The timer counter 1 has 2 registers. They have register A and they also have register B. Because they're 16-bit, they actually have 2 registers. So this is an 8-bit register for control, and the other one is another 8-bit register. And it gives you a few switches that you can turn on and off to control different aspects of the timer counter. When you're looking at the data sheet, it's actually not that difficult to understand. You'll see these descriptions here, the COM1A1, COM1A0, and so on. And you're going to be using this in your programming. You can actually go to the data sheet and actually say, I want to control this bit, the COM1A1 bit, and we can use our bitwise operations of shifting, as you'll see while we're doing our programming, to control that bit. Just for reference, this is on page 107, and the control register B, which is over here, we'll be using mainly the CS10 immediately. That is on page 110. To invoke the timer or start the timer, we're going to go ahead and use the CS10, and we're going to put a 1 in that position. So we have the clock started, and we're not going to be doing any pre-scaling. Pre-scaling is actually really easy. So I'll talk about that in a little bit. But right now we're just going to use no pre-scaling. It's going to count with the clock that's internal with the AVR chip. So let's go ahead and start. I'm just going to go right into the programming. By now you should know how to get here. I generally just use the main C under LED on. So we're starting out with essentially just a shell of a program. I'm including the standard AVR IO.H, and I have my main block, and I also have my while block. I'm going to write in a couple comments of what we essentially want to do. Here I'm just going to initialize the port for the LEDs, and inside this while loop I'm going to count and turn an LED on and off. And before we get into the details of making it blink every single second perfectly, we're going to experiment a little bit and just sort of get to know the counter and controlling the counter. To prepare the LEDs for output, or the ports that we're going to be using, we are using port B and port D, but I'm just going to use one port for now and one LED on that port. DDRB, the data direction register for B, we're going to have that equal to 0B, let's see how many, 1, 2, 3, 4, 5, 6, 7, 8. We'll just do the one on the end as output. And then we're going to have port B equal to zeros all the way across, since we want the LED to be off when we start the program. We need to also control the timer, and we're using the timer control register, so T timer counter control register
and this is going to be 1. And we need to know which register to go to, the A or the B. When I looked at the data sheet before, it was the B, so I'm just going to put B here. And that's the particular register we're going to be using for controlling turning the timer counter 1 on and making it have a pre-scaling of 1, which it means it's going to tick in rhythm with the clock, the internal clock. So let's go ahead and just use the shift, and we can use the OR equal bitwise operation 1 and shift it, and we're going to be doing turning on the CS10 as we saw in the data sheet. Now we're going to go to the never-ending loop, and we're going to check for how Mr. TCNT1 is counting. Mr. TCNT1 is a 16-bit counter, so that means he can count up to 65,535. Let's test a few numbers just to have some fun. So we're going to say if TCNT1 is greater than, let's say, 10,000. Let's toggle our LED. The first thing I want to do before I toggle the LED, however, is I want to make TCNT1 to be 0. Because if I don't make that 0, that means it's going to continually try to count all the way up to 65,535, and then it'll go back to 0 again. I want it to go back to 0 at 10,000, and then count up to 10,000 again, and then have a nice equal counting. So we're going to toggle port B, and that is using the exponential sign, and we're going to be doing this to pin 1. I forgot my pin B1. I just put pin 1. What I need to do is I need to insert a B there. This should actually be pin B0, because if you look over here, I'm using the 0th pin, and to be able to use the pin that I'm having direction out, this one is actually pin 1 is over here, which is 0, and that's not going to really do anything. I'm going to go ahead and try to. Okay, now we're going to program.
So what we've just done is we took a number that is 1 million, which is the internal clock, and every 10,000 times it's going to blink. So let's see how many times per second that is. So this should be equal to, let's see, that's 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, so that's 2 zeros left over. So the LED is actually blinking 100 times per second, and that's probably fast enough to make the LED look like it's constantly on. Because we have a pretty clean number here, we have 100 times per second, we could probably get down to maybe 10 times per second, or we can get down to 1 time per second, which is every 1 second, by introducing another loop. So we could say, do this. Go ahead and do the count to 10,000 100 times, and then turn the LED on or off.
So let's introduce another integer, or let's introduce an integer called repeat count. And this is going to initially be 0, which is the default anyway, but it doesn't hurt to put it in. And then over here, we're going to say repeat count, and we're going to increment it 1. And when this repeat count, if repeat count is greater than 100, then it will do the, we got a couple things to put in here. It will do the toggling, and it will also reinitialize the repeat count. So repeat is now equal to 0 again, so it can do this all over again. And we end our block, indent it correctly. So now we have the 10,000 being counted under the 1 megahertz, and then we're going to repeat that 100 times before we have a port B change. So theoretically, we should have a blinking every second or so. So let's try it. I'm going to go ahead and do the make and program. So do the make and program as we've been doing it normally. From now on, I won't be showing the making and the programming, and I'll just show the response from the circuit.
Our theory stands pretty true. It looks like it is blinking every second. So our program is successfully working. Although, if you try to time this, you will be 10% off either direction or maybe right on, because the internal clock is not that accurate. So there you go, you have an LED blinking every second. Now let's do the chasing of these LEDs. Seventh of a second, and then these LEDs will chase every second.
Before I go on, I'm going to introduce you to another variable, and it's called UINT8, actually, UINT8 underscore T. So this is a version of the integer variable declaration that is only 8 bits long. We know our repeat count is not going to be very high. It's not going to go over 255, which is the maximum for an 8-bit number. So we can safely say this is we don't really need anything more than an 8-bit integer. So we'll just go ahead and do this. And even if it was unsigned or signed, it still won't even go over the signed version of the 8-bit integer. Unsigned means that an 8-bit integer will go from 0 to 255, and it will always be in the positive direction. An signed integer will be in the positive and negative direction, but it has to split the 256 into 2, so it'll have 128 on one side of the number line and 128 on the other side of the number line. So it'll be able to go from negative 128 to positive 128, which equals 256. I'm going to get rid of this since we don't need this anymore. Okay, so since we need the LEDs to be chasing, I'm going to bring in my favorite LED number variable, but I'm going to make this the UINT8 underscore T again, and the LED number, and it's going to be an array again of 2 because we have the LED in port B, the LED array in port B, or all of the LEDs in port B, and we have all the LEDs in port D. But the LED number 0 will be port B, and the LED numbers under 1 will be under port D, just like we had in the previous video. Okay, what I want to try to do this time is the repeat count is actually our own form of pre-scaling. And let's just go ahead and get rid of the repeat count and enable the pre-scaling that the AVR chip provides us in its features. Let's take a look at the data sheet and see what options we have. The control register that we need to focus on is the timer counter 1 control register B. The A doesn't have the pre-scaling information, but the B section of this 16-bit register does. So let's just take a look at the pre-scaling. You can see that we have the CS10 that we used before has 1 pre-scaling, or no pre-scaling, it's just essentially 1. And the CS11, if you turn that on and have both CS12 and CS10 off, you have pre-scaling of 8. 64 is if the 10 and 11 is on. 256 pre-scaling is if the 12 is on. And 1024 is if the 10 and 12 is on. So let's actually learn a little bit about pre-scaling.
Just like in a regular clock, you're going to have ticks. And in the AVR, it's going to tick 1 million times per second. So you got tick, 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 tick. And as it's ticking, the counter, Mr. TCNT1, or Mr. TCNT1, will tick along with this internal clock as it's ticking away. In pre-scaling, if there's no pre-scaling, it's going to tick with the internal clock. If it has pre-scaling of, let's say, 8, the TCNT1, Mr. TCNT1, only counts when the internal clock has ticked 8 times. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. So it'll count again here. 1, 2, 3, 4, 5, 6, 7, 8. It'll count again here. So every time the internal clock ticks, if it's pre-scaling of 8, it'll have 1 here, 2 here, 3 here, and so on. And that's the same thing as the pre-scaling of 64 or 256 or 1024. And what that does is it slows down the TCNT1 enough so it's more compatible with the scale of like the clock that we're essentially used to. Let's determine what prescale we need. We know that the AVR chip will count up to 1 million every second. So if we use a prescale that Mr. TCNT can count up to, that covers the entire quantity, then we'll be okay. So if we, let's say, we know that TCNT 1 can only count up to 65,535. So if we see how many parts 65,535 into 1 million, if we just divide that, divided by 65, we will know what prescale we generally need to be. And this is equal to somewhere around 15.3 or so. This number essentially tells us the lowest prescale that we can use. Now we know that 8 obviously won't work because this is higher than 8. So we're going to have to go all the way up to 64. So 64 prescale is a number that the 16-bit TCNT, Mr. TCNT1 will be able to handle. So let's find out what the number is when we take 1 million and divide that by 64 and see this will be the number that Mr. TCNT1 will have to count up to. And this comes out to be 15,625. Mr. TCNT1 will have to count up to 15,625 and then reset itself, and we can do our LED toggling. But we also want to toggle. We want to do the LED chasing for every 1/7 of a second, and then the port D we want to be able to chase it every second. Do an LED chasing every second. So we need to take this number. We need to divide it by 7. So it looks like we have 232 or 2232. 2,232.142 or 143 actually. So we're just going to go ahead and use a number 2232, and every time we have the 7 LEDs on port B lit up or chased, we will move the port D LED. So let's go ahead and give that a try.
So now that we know that we're going to be using the clock prescaler of 64, we're going to have to set CS11 and CS10. So let's go ahead and do that. So at this location we have the TCC RB, which is the timer counter control register, and this is the timer counter 1, which is the 16-bit version. We're going to go ahead and add another shift, OR-ing. We're going to shift the CS11 as well. So we're turning on 11 and we're turning on 10. Alright, so since we are using the internal prescaler, we can get rid of ours. We don't need this one anymore. Okay, and we don't need the repeat count anymore. Okay, so, and we have determined that our number here needs to be 2232. 2232. We can also get rid of this one here. Okay, so every time it gets to 2232, it's going to reset itself, and it's going to toggle pin 0. We don't want to do this. We want it to chase. So we're going to be using the LED number variable and the array number 0, and that should work. Now we want to also add that if the LED number of 0 is greater than 6, then it does the same thing to LED number on the port D, which is LED number 1. That's set. Okay, so we're going to go ahead and say LED number 0 is equal to 0, so it resets itself, so it doesn't keep counting up. And the port D is equal to shifting the register. I have to change the one just above it. Shifting with LED number 1. And we're going to increment LED number 1. Okay. And if we need to make sure that on port D, when it gets to the last LED, it goes back to the first LED. So if LED number 1 is greater than 6, then it simply resets itself. It's equal to 0. I still need to make that equals instead of the XOR. I also just realized that I can't use the uint8 with arrays, so I'll just go ahead and use the standard int that I usually use. I also noticed that I forgot to increment the LED number 0, so let me go ahead and do that. So every time we are counting up to 2232, I also need to increment the port B side of the LEDs. And because we are working with all of the LEDs now, we want to make sure they're all set to output. So we should have the first one 0 because we don't have an LED on that one, and then we should have 7 1s. Okay. We are also bringing port D into it, so we need to set up port D, DDRD, equal to 0B, 0, and then 7 1s. And port B, port D, should be equal to 0s. So we'll make sure they're off. Okay. Go ahead and make all and program.
Okay, so after programming, we noticed that the set of LEDs, the port B, is counting up 1/7 of a second, generally, or approximately, and this is approximately counting up every second.